Hey everybody, welcome back. We're going to talk a little bit about circular orbits and weightlessness, a little bit of gravitation and orbiting objects and kind of how we got there. So to start things off, we're going to start with a little history lesson with some pretty famous names that I'm sure you've heard of before. A lot of this goes back to Copernicus. So Nicholas Copernicus was one of the first, or the first, to come out publicly anyway and say that the planets in the solar system revolved around the sun, which at the time was a very, very big deal because it was going against the teachings of the church, and he was at risk for being killed for stating that publicly, and he kept it in for a very long time for that very reason. So moving on, that was a big realization because that allowed further progress to be had. So from that point, I'm kind of skipping and jumping here over long periods of time, but Johann Kepler is another very important player in this evolution of understanding of orbits and the solar system and beyond. But Johann Kepler realized or discovered that the planet's path was not circular. It was actually elliptical. And mathematically, that made a very big difference. And it was one reason they had trouble making some of the calculations and being accurate for how long it takes, say, the Earth to go around the sun or other planets to go around the sun, or the moon to go around the Earth, and things like that. So once that was established, that planets actually moved in elliptical orbits, mathematically that allowed for a lot of advances in calculations and therefore understanding of our solar system and of other objects out in space and how they operated. Then comes along Isaac Newton. Now, he had already come up with this idea of gravity, of why things fall, that there was a force pulling things towards the center of the Earth. And once it was established that everything orbited around the sun and that those orbits were circular, it allowed, or elliptical, I'm sorry, it allowed him to expand his thinking to not just say that objects on Earth fall in a certain way, but to expand it to say objects anywhere can potentially fall in the same way that objects on Earth fall. And that was a big deal because Aristotle believed that different types of motion occurred because of different things happening to those objects. And so Newton really put this to a general sense and said, don't be so specific. I'm going to look broad and say that there has to be some unifying factor. This force of gravity could be the unifying factor with how everything moves everywhere. And that is such a huge, huge thing. So, Isaac Newton, he came up, or had a little thought experiment. And this thought experiment is called Newton's cannon, and it involved a cannon on a really big mountain. All right, so maybe I'll just draw a big cannon. So I'll have a really big cannon. This is Earth. And we have this huge cannon. There we go. All right, so if you fire a cannonball, and this is the same thing if you throw something, if you kick something, launch something, fire something at a certain velocity, that object, whatever it might be, will simply fall to the ground. Oh my goodness, why does it keep doing that? Okay, whatever. You understand. And so his thought experiment said, all right, well, if you now increase the velocity, that you fire this object, then what will happen? Well, it might go a little farther, but eventually gravity is going to pull it down and it's going to hit the ground. So he extended this and took this to an extreme case and said, well, if you fire it at a high enough initial velocity, what should happen? Well, the object will keep falling, but because of the curvature of the Earth, it will continue falling forever. All right, so this was Newton's canon. This was his thought experiment. And so this idea was revolutionary. And it really paved the way for the idea of orbital motion. Because in fact, that is what is happening. If you launch something fast enough and there is an exit velocity that we need to launch a satellite on Earth so that it goes into orbit. All right, if you think about it, when we talk about projectile motion, and we say, what are the forces at any point? What is the net force at any point along the path of a projectile, right? All it is weight. That's it. Only weight. And so that is what's happening when something is in orbit. It is being pulled to the center of the Earth at all times with some force of gravity, but because of the curvature of the Earth, it continuously falls. And so we use that idea as we go forward. All right, so let me move this so we can kind of move this around. All right, so if the launch speed is high enough, then there comes a point that the trajectory and the curve of the Earth are parallel, and this is what you get. So you get a something that is in orbit. So an orbiting projectile is in free fall. That is what is happening here. Okay, anything that is in orbit is actually in free fall. The only force acting on it is the force of gravity. Okay, so force of gravity is the force that causes the centripetal acceleration of an orbiting object. All right, so that's important here. So if we set up Newton's first law, or Newton's second law, so this is on your equation sheet, all right? Acceleration of an object is equal to the net force divided by the mass. Okay, well, if the net force is the weight, that is the only force that is acting, and we know the weight is equal to mass times the acceleration of gravity. M's cancel, and look at that. The acceleration of an orbiting object is equal to the acceleration of gravity. And there you go. All right. And now we can look at this and say, okay, if we extend this to the idea of centripetal acceleration, this is another equation on your equation sheet, right? Always keep tabs on these equations on your equation sheet. They are of utmost importance. So the velocity of something in orbit, and remember, it's v squared over r. And the acceleration, oops, where am I? Oh, yeah. And that, of course, equals the acceleration of gravity. And then if you rearrange that, you could then say that the velocity needed for something to be in orbit is equal to the square root of the acceleration of gravity times the radius of the orbit, which is, in this case, the radius of the planet from the center of the planet to the altitude that you are orbiting, if that makes sense. Okay, So the radius now kind of has two parts if we're talking about a planet. Now, consider this. The first two equations that I starred right here are on your equation sheet. All right, getting to the fact that the acceleration of something orbiting equals the acceleration of gravity, you can work your way through this to end up getting that. This equation down at the bottom is derived from this middle equation, all right, and the top one, I guess. So this bottom equation is not one that you should memorize, okay? You do not need to memorize it. Don't waste brain space memorizing this equation. If you try and waste brain space memorizing every single equation that you see this year, you will just have a brain full of equations and not much use for them. Understand how to get to this bottom equation, starting with the two equations that are on the equation sheet, because the equation sheet equations are in front of you. So always start with something on the equation sheet. Use your understanding of the concepts to then get to some of these secondary equations. If you can do that, you will be much better off. All right, so the orbital speed of a projectile, let me move myself out of the way here, that is just skimming the surface of the Earth, right? So this is from the center to the surface. If we got rid of air resistance and it was smooth, there were no mountains and all of that, would be, based on our equation that we just derived, would be about 18,000 miles per hour. Okay, that's how fast you would have to go on the surface of the Earth if we got rid of all the air and there were no mountains in the way. You would have to go about 18,000 miles an hour to not fall and hit the ground in order to keep falling around the Earth. All right, so you can do this for any period, we can do this to find out the period, how long it would take for something orbiting the Earth based on this equation. Okay, again, not an equation you need to memorize, but one that you can get to logically from some things that you know, right? 2 pi r is the distance around a circle, times the t period is the time it takes to get there. If we rearrange this, velocity equals 2 pi r over t, we had that equation with circular motion, simplifies to this. All right, so the time it takes to go around an orbit is only based on the radius of the orbit and the acceleration of gravity. Okay, which, think about it, the acceleration of gravity will change based on the height that you are orbiting. That's important. All right, so astronauts, when they are up in space, International Space Station, they are in free fall. And that is what causes the weightless feeling. All right, when you jump off of a platform or at a pool, or you jump off of a cliff into a lake or something like that, you feel that free fall feeling, that weightlessness. That is what the astronauts feel all the time. Now, it doesn't necessarily feel like they are falling the whole time, right? It doesn't feel like that, but that is what is happening to them. All right, so the moon is considered a satellite. All right, a satellite is anything that orbits anything else. So the moon is just falling around the Earth. So if you use the distance of the moon, which is that distance right there, it's about 300,000 kilometers. And we can calculate the time it takes to go around. Now, this says if you do that, you get 11 hours. And the reason for that is the acceleration of gravity that the moon feels is not what we feel, because the moon is a lot farther away from the center of the Earth. So the acceleration of gravity decreases. Okay, so this feeling of weightlessness, we've talked about this in regular circular motion. When you're in contact with the surface, or an object is connected to something else, right? But in this case, if you're going through the bottom of a hill, that normal force you feel heavier. If you feel weightless, that normal force is very small or non-existent. And if you are in free fall, it is non-existent. All right. So just a brief introduction